Well, hello. I want to give you a little bit more background information on chemical equations and chemical reactions. In this unit, we are going to learn, and you maybe already watched the video on how to balance equations. We're then going to learn to classify equations, categorize them, and then we're going to learn to write word equations. Once we feel real comfortable with that, then we're going to start the mathematics of the chemical equations. That's called stoichiometry, our next unit. But I want to give you a little bit more background information before we continue. So this might help you organize your thoughts. When we're talking about chemical reactions, under chemical equations, we learned how to, in the earlier video, balance chemical equations. Then we're going to learn how to predict the products from the reactants. And that's going to be coming in maybe a couple more days video. And then in terms of classifying chemical equations, we'll learn there are some called synthesis and decomposition and single and double replacement and combustion. And you'll be able to just look and in a split second figure out what type of reaction it is. At least that's my goal. So we know a chemical reaction has taken place perhaps if we observe some of these things. These are indications of a chemical reaction. It may not be a chemical reaction, but it's a very good indication that there is a chemical reaction taking place. Here they are. If you mix chemicals together and you get an amount of heat coming off or light or sound, that's probably an example of a chemical reaction. Think about maybe a hot pack or a cold pack. You squeeze it or shake it and it either gets hot or cold. There's a chemical reaction going on. Or maybe a light stick where you snap it and it starts to produce light. Those would be examples. If something produces a gas, if you dump two chemicals together down a sink and it starts making a green gas or a brown gas or a red gas, that's generally indication a chemical reaction is taking place. Or if you dump together two liquids and they form a solid, what's called a precipitate, little chunks form in there, that's an indication a chemical reaction is occurring. So here I have a clear liquid poured into another clear liquid, and it produces this yellow precipitate, this yellow solid. And so when I say color change, I'm thinking colorless plus colorless makes yellow. That indicates a chemical reaction. Now, if you simply add red paint into white paint and it turns pink, that's a physical change. That's not any color change indicating a chemical reaction is occurring. All right, let's continue here. We could watch this little video. Let's see if it's active, if it works for us. No, it doesn't seem to work, but we'll look at some of these where we'll take colorless and get some different colors later. All right, so I've summarized that for you here for some of you that are a little bit more visual. If something changes color, so this is changing colors, that's an indication maybe a chemical reaction is taking place. If there's a change in odor, right? Maybe you know that food, you know what food should smell like, and then if it smells kind of funky, well, there's a chemical reaction taking place. That food has gone bad, so a change in odor, a little skunk to remind us that. Well, that little skunk might spray you, and that's a gas or vapor coming out, right? So again, if you mix chemicals and they produce a gas, that's oftentimes indicative of a chemical reaction. Input or release of energy, what that means is when you mix stuff together, it gets either hot or it gets cold. So energy is either going to be going in or coming out. So if it's going in, it's going to be feeling cold because it's taking energy away. If it's releasing energy, it's going to be feeling hot as the system is releasing energy. Now, chemical reactions have a direction. They go only one direction, from reactants to products. So they're difficult to reverse. Now, this was a harder one for me to come up with, but I think I came up with two okay examples of things difficult to reverse. One of them is pregnancy. You either are pregnant or you're not. You can't kind of become unpregnant by reversing that process. Or here's another example, getting older, right? Unfortunately, life moves on and we get older. We're not like Benjamin Buttons and we can get younger. So these are all signs of a chemical reaction taking place. All right, let's make sure we know some vocabulary. What you start with in a chemical reaction is called the reactants, and what you end with is called the products. So here I have a balanced chemical equation. Aluminum plus oxygen makes aluminum oxide. Now, aluminum, we know what it looks like, kind of a silver-looking metal, very lightweight, might be used in ductwork for your dryer. Oxygen's a colorless gas, and it can produce aluminum oxide. It looks kind of like this. Now, for us here, if you grind up aluminum oxide, it makes this dust-looking stuff, and if you glue that onto paper, we call that sandpaper. That's what sandpaper is, aluminum oxide. Now, in terms of the aluminum and the oxygen are the reactants. That's what you start with. And what you end with is always called the product. It's what you produce. And we know, based on what we've seen so far, that atoms are rearranged in a chemical reaction. So on the reactant side, we have 4 aluminums represented, and we have 4 aluminums on the product side, 2 times 2. On the reactant side, I have 6 oxygen. On the product side, I have 6 oxygen, 2 times 3. So it's a balanced chemical equation. The atoms are simply rearranging into new combination. That's what a chemical reaction is. And when they do rearrange, they tend to have different properties than how they started. Now, the letter S here refers to solid. Aluminum is solid as I've reacted it. The G, a gas. If I use the letter L, that would refer to liquid. And those are simply the physical states the compounds are found in. The numbers in front, the 4, the 3, and the 2, would be the stoichiometric coefficients. Stoichiometric or stoichiometry refers to the math of chemistry, so anything with numbers is called stoichiometry. The coefficients represent how many of each of the items we have. We have 4 aluminums, 3 oxygen molecules, and they produce 2 aluminum oxide formula units. Now, this doesn't work math-wise. Some of you are going, well, 4 plus 3 is 7. That doesn't equal 2. No, you're misunderstanding. It's referring to the number of things you have. And when they get rearranged, they can have different combinations. So it will work out. We'll look at the math of that later on. All right. So if we were to interpret this as saying 4 grams of aluminum plus 3 grams of oxygen yield or produce 2 grams of aluminum oxide, that is simply incorrect. That would violate the law of conservation of mass. There's no way that 7 grams can just disappear into 2 grams. So instead, what that does mean is it could be 4 aluminum atoms plus 3 oxygen molecules will produce 2 molecules of aluminum oxide. That is a correct interpretation in the simplest terms. Generally, though, we don't work with single atoms or just a handful of molecules. We work with much larger groupings called moles. So an alternative way to interpret that equation is this. 4 moles of aluminum will react with 3 moles of oxygen to produce 2 moles of aluminum oxide. And if we wanted to do the math there, let's do that. 4 moles of aluminum, each aluminum weighs 27 grams per mole. I have 3 moles of oxygen, O weighs 16, so O2 weighs 32. And 2 aluminum and 3 oxygen, aluminum oxide, would weigh 102 grams if you took the time to add that up. Now, do the math. 4 times 27 over here is 108. 3 times 32 is 96. 2 times 102 is 204. And even without a calculator, I know that 108 plus 96 is going to equal 204. The mass must be conserved in a chemical reaction. That's the law of conservation of mass. So the proper way to interpret those coefficients is either think of them as atoms, molecules, or moles. One of the two. It's not a gram coefficient. All right. We know that in a chemical equation, atoms at the beginning, on the reactant side and on the product side, have to be the same. They're not destroyed. They're not made, they're simply rearranged in a chemical reaction. So the amount of matter in that system that we're studying does not change. That is the foundation of the law of conservation of matter. Now, the law of conservation of matter was espoused by Antoine Lavoisier. He's shown here with his wife. And because of this principle, it makes sense that the atoms that you start with on the reactant side and the product side are the same. They don't change. And therefore, the equation must be balanced to indicate that. So it must have the same number of atoms and the same kind of atoms on both sides, the reactant and the product side. Now, we've looked at characteristics of chemical equations earlier, but let me just remind you of a few things. The chemical equation must represent known facts. In other words, when you write a chemical symbol, it has to be the proper symbol and the proper formula. So the equation has to have the correct formula of reactants and products. So if you write water, it has to be H2O. If you need an extra something like, let's say we say H2 plus O2 goes to water. Now, that's not a balanced equation. I have 2 hydrogens on the reactant side, 2 on the product side. That's great. But I have only 1 oxygen, I have 2 oxygens on the reactant side, but 1 on the product. Now, I am not allowed to simply add a subscript 2 down here because that doesn't represent known facts. H2O is water, H2O2 is hydrogen peroxide. So you're never allowed to add a coefficient, a subscript on there. Instead, what we would have to do is add coefficients. So I have an even odd, I have 2 oxygens and 1 oxygen. So if I add a coefficient 2 here, now that gives me 2 oxygens on the product side and I have 2 on the reactant side. Of course, now I have 4 hydrogens on the product side. So I'm not going to change the subscript 2 on the reactant side to a 4. Instead, I'm going to add a coefficient 2. So now I have 4 hydrogens on the reactant side, 4 on the product, 2 oxygens on the reactant, 2 oxygens on the product. That's what I mean when I say it must contain the correct formulas for the reactants and the products. And by doing this, the law of conservation of mass will always be satisfied. That's a very, very important law of nature, especially in chemistry. Now, we've used this term, but I just want to remind you, reactants are what you start with. They're what happened before the chemical reaction takes place. The products are whatever it forms into during the chemical change, the new substances. So the chemical equation is going to indicate both reactants and products. So reactants turn into products. That arrow indicates a chemical change or chemical reaction has occurred. All right, we're going to get into word equations here, and word equations are going to be a little bit different. They're going to be describing the chemical equation, but not using formulas, but using the words. Now, we'll actually spend more time on this, but I just want to introduce it. So it says a word equation describes the chemical change using the names of the reactants and products, right? So let's see if we can try one just so you get the feel of this. Now, the advantage of a word equation is you don't have to know how to write the chemical formulas. The disadvantage is it's not going to be qualitative, it's only going to be quantitative. But let's try one just for fun. Write the word equation for the reaction of methane gas with oxygen gas to form carbon dioxide and water. So it looks like we're reacting methane plus oxygen. So it says reaction of methane gas and oxygen, that with means plus, to form, well, the phrase to form means arrow, and then we're forming carbon dioxide and water. That is the word equation. Now, it doesn't do us a lot of good because we really need to know the chemical formula. Now, methane's one you might not know. it's CH4. Well, let's continue here. This, of course, are my reactants, and these are my products over here. Now, if we wanted to, we could write out a chemical equation. Methane is natural gas. It has the formula CH4. Oxygen is always diatomic. It is O2. And then carbon dioxide, that's the two nonmetals using Greek prefixes, is CO2. And of course, water is always H2O. Now, we would want to balance that. As I start on the reactant side, I have one carbon. On the product side, one carbon. On the reactant side, I have two hydrogens. On the product, I have two. So I went from 4 to 2, so I would need to add a coefficient 2 in front of the hydrogen. Now, I have two oxygens from the water and two from the carbon dioxide, so that's 4 oxygens. And I've only got 2 on the reactant side, so I need a coefficient 2 there. At that point, we have a balanced chemical equation. Okay? All right. So you can now see the difference between a word equation and a chemical equation where we use the symbols. And generally, the symbolic representation will be more useful for us. I want to just show visually a chemical reaction taking place here. Now, what we're looking at is the reaction between sodium metal and chlorine gas to make sodium chloride. So I'm starting with the silver circles represent 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 moles of sodium. Now, for the chlorine, I have 1, 2, 3, 4, 5 moles of chlorine. And what they're going to do is react. And we're making NaCl. We don't really know how much we're going to make, but let's visually figure this out. Remember, there's going to be a rearrangement of atoms. So there's going to be a sodium combining with a chlorine. That makes one NaCl. Well, that leaves you an extra chlorine, so an extra sodium would have to join that. Now we have 2 NaCls, but we still have more sodium and chlorine, so we're going to continue. We'll take another sodium and a chlorine. That leaves us another chlorine and another sodium. We still have more reactant, so we keep going. Another NaCl, another Cl with an Na. Still have more, so they're still going to continue to react. And you can start to see, and chemical reactions do take time. It's not instantaneous. And finally, we have an Na and a Cl and an Na and a Cl. Now, if I take the time to count how much salt I produced 10 representative moles of NaCl. So I could take those coefficients, and that ratio 10 to 5 to 2 reduces to 2, 1, 2. So generally in a chemical equation, you always want to have it reduced like I've done here. And so I can show that we're taking 2 sodiums plus 1 chlorine molecule to make 2 sodium chloride. All the rest of that is just extras, right? If you were making a batch of cookies, you find a recipe. If you want to make more cookies, you simply increase the amount of each of the components. And really that's what we're showing here, just the simplest recipe to make sodium chloride. All right, I think I already went through in an earlier video how to interpret these formulas. H2O is simply a single molecule of water composed of 2 hydrogens and an oxygen. If I have 2 of them, I use a coefficient 2 to represent 2 molecules of water, and that would be composed of 4 hydrogens and 2 oxygens. If I instead wrote this or drew this, this represents a single molecule composed of 2 hydrogens and 2 oxygens. That happens to be called hydrogen peroxide, and it's quite a bit different than, this little 2 down here is very different than the 2 up here. They mean something very different. So let's make sure when we balance equations, we only use coefficients. Never ever change the subscript, because that changes the substance that you're dealing with. All right. I think we've already gone through the balancing equations, so I'm not really going to worry about doing that with you at this point, right? we had some rules, we applied those rules, and we got pretty good at doing that. And I showed you a little trick why you do this single element last. Go ahead and review that video earlier on balancing equations if you have questions about that. All right, I'm going to go through, this will be the last example on this particular video, and then I'll start another one to kind of continue. Now, let's look at this equation as it's written. It says ammonium phosphate plus magnesium hydrate produces magnesium phosphate. Now, I'm hoping that that looks very odd to you. And the reason it looks odd is we have violated the law of conservation of matter. We've lost matter. We started with, in this case, ammonium phosphate and magnesium hydroxide, and we formed magnesium phosphate. So what's missing? Well, it looks like the ammonium and the hydroxide are missing. So we would need to add those, and that is our new product, ammonium hydroxide. Now, if you wanted to, maybe you remembered ammonium is NH4 1+, and hydroxide is OH1-. They have the same charge. They can get directly together, NH4OH. Now, at this point, we have an equation, but it's not balanced yet, is it? Now, on this one, we got lots of places we can start. Remember, we said start with the polyatomics first. Well, I've got ammonium and phosphate and hydroxide. I got a lot to play with. So I'm just going to go ahead and start with, I'm going to read from the right. I have 3 NH4s. So I'm going to go ahead and put a 3 in front of the NH4. Now, even if you follow the rules, I would always suggest you do it with a pencil, not a pen, because sometimes you might have to erase some things. Let's keep going. Now, I have 3 OHs, but on the reactant side, I have 2 OHs. Well, that's an even-odd situation. So what I'm going to do, I could fix it from here. I could say, well, 3 and 2, the number they have in common is 6, so I need to put a 3 here, and that ammonium hydroxide, instead of a 3, we said we need to have 6 OHs, so I'm going to go ahead and put a 6 in front. Now look what that does. It gives me 6 ammonium, but on the beginning I have only 3 ammonium, so I need to put a coefficient 2 there. Now I have 6 ammonium, and I have 6 ammonium on the product side. I have 2 PO4s on the reactant side. I have 2 PO4s on the product side. I have 3 magnesiums on the product side, 3 magnesiums on the reactant side. So now we have it balanced with the coefficients 2, 3, 1, 6. Okay? 2, 3, 1, 6. All right. I'll give you one to try here. Go ahead and pause the video at this point if you want to try it, and then come back and I'll explain it. We can double check. All right, welcome back. Hopefully what you did is you saw the 3 carbonates on the product side and only 1 carbonate on the reactant side. So you should immediately put a coefficient 3 in front. Now at this point, you're going to be like a cat chasing its tail. You have 6 lithium on the reactant side, and so you need a coefficient 6 here. Now that gives you 6 chloride, and you only have 3 on the reactant side, so you put a coefficient 2 to get 6 chlorides. That gives you 2 aluminum. On the reactant side, you have 2 on the product side. You're all done. All right? Good job. All right. Thanks for joining me. I'll stop this video here and make more to try to explain this all to you. Take care. Bye-bye.